that integer argument. So basically, whatever that name is, whatever that the argument can be called, they are all kind of run here. We want them to run here. The API is not really anything that is a secret. You can have the API coded directly here. The idea is that INT128. INT128 is the entry to the kernel space. Okay, so that's why we need to have interrupt call. So interrupt call is not say, oh, that's for interrupt-driven device drivers, also for the service entry. And this will have a mode change. Okay, this will change the user mode of the process runtime. So what's mode? Mode is the CPU mode. Okay, CPU mode. And then from the change this from user to kernel. Okay, kernel. And that's the Unix convention. Only have two modes. Okay, user mode. That's when you log in, and then the login process assigns you into the user mode. So, like the real system. And then whatever you run is the user mode process inherited from the parent. Okay. And desktop manager, GUI, whatnot, they all started from the login, getting the interaction shell of desktop manager. Okay. And then this login is privileged process that can set both to the new processes. When you fork a child process shell, you actually can change mode to the user mode so that you log in, because your UID and password shows that is a user login. It's not the root in the Unix Linux convention. So that's the user mode assigned to what? Again, to the CPU. Okay, mode is not a software. Mode is a CPU. CPU flag. In the CPU, there's an E flag. Okay. So they are flag as a flag. A user mode indicate is the flag indicates a user mode or kernel mode. More about this later. So that is hardware we cannot set by assembly code program ourselves. We got to go in change mode by the interrupt call. The interrupt call is a circuit. Okay, so people say, oh, that's the interrupt gate. And that's the gate. Once entered, CPU enter this gate, got a mode change to execute into the service code by the IDT mapping. Okay, so IDT is also in kernel space. You cannot alter it. The user program cannot access it. Okay, and therefore there's no way that the user code, you write code, want to set the mode change in the CPU hardware or alter anything in the kernel space, because kernel space are protected by the mode. Okay, so you say, okay, how can I, access anything over this side? You cannot. Why is that? Because any access done by the memory management translation from virtual to real address, according to the table of the translation, got to require that mode. But your CPU currently doesn't have that mode. That means your ADAL, you write a program, want to access kernel space, cannot, even however you try. Okay, so and then you cannot use a program, your own code, to alter the mode either of the flag here. Okay, so then you can see the only way to get in is through this, and this is the interrupt gate, the circuit that will change mode, but it will only come to the kernel service code. It's not going to be in the user code. Say, oh, we're going to execute your code now after we interrupt 128. That's not possible because your code is not here. Okay, otherwise it will have the malicious code right here. Yeah. So hacking is to change the kernel code. Okay. So people say hacking is to change the kernel code, and especially in the DLL in the Windows. A lot of service codes are in the .dll file. And that's inherited from, that's not Windows invention, that's inherited from the shared object of the Unix world. They call it shared object files. So that's the frameworks. Okay, whatever fancy frameworks you use, so you got to install. And the install say, oh, you got to be in the root user login to where's the login? So where's so that's the login assign the user to be the root login, and then you can install. Oh, it requires the administrator password, right? So every time you install something like what? Something like that infamous Adobe Flash. Okay. Every week they have an update. Every week they ask you to enter the administrator password. And every week that Steve Jobs complained about this when he was alive. But nobody knew what he was talking about. Why he's so mad about Adobe Flash? Because it doesn't need to be that way. They did it, like this, too lazy to change that. Like Firefox never needed that. Okay, certain software user mode install is totally doable. Why does it need to be administrator mode? And then who knows why it's trying to install, Okay, so it doesn't affect the OS DLL, okay, just install the application DLL, okay, in the directory that's only allowed to be changed by the administrator password, or can be used in the user space, okay. And there are install DLL space. One is the user side, one is the kernel side. User side doesn't require administrator password, but still apply it to the user runtime of user applications. Okay, so this basic all of the security 101. So then so that's the reason why Steve Jobs never liked Adobe Flash, and then people back then didn't understand what he was talking about, and so Adobe kind of refrained themselves. After Steve Jobs commented that once on TV, Adobe update doesn't appear that much anymore. And then once he died, then boom, come back to life again, even worse. So was Microsoft. Anyway, so yeah, that's the situation we are in the struggle between business and the actual security. Yeah, so Facebook facing that. Nobody's laughing anymore. Okay. So you got to kick in from you got to learn things from the basic. What is computer security? It starts from CPU. CPU computer security is the first wall we built, the last wall of defense. Okay. So it's not outside guessing password. Enter from the door with that password. It's yeah, so I hope you understand this. To be a real computer guy about computer security, you got to see that has totally to do with hardware and OS. The architecture provided just the thing, just a single bit. No matter how you do, you cannot change it. You knock it with a big hammer, you flash it with a laser light, it just won't change. Okay, it will destroy the whole computer. Still, you cannot change that single bit. Strangely enough, right? All you want to do is change that single bit in the CPU, so that all the runtime execution becomes you are privileged to use whatever instruction you want to change whatever you want. Okay. So so here the IDT table, is also part of Bootstrap initialized. It has a jump point for 128 into 128 go to the requests, and the hardware trigger also go into the kernel. As a device driver needs to, okay. Also from here, trigger the IRQ signal, and then go into the services. You see, that is how the security comes. But you see, right now we are all running in the user mode. You can access from the user proc, child proc, get the run pip directly. You can print run pip directly. Why did you need to call the sysget pip? Or get PPID, doesn't make sense because we haven't separated the user and the kernel space yet, unless we have virtual memory. Okay, once we have virtual memory, the virtual memory address is translated by the translation table, and this translation table is the kernel space, and can only be accessed by the privileged process. And during the runtime of your program code, MMU is a piece of hardware will take whatever CPU wants to fetch instruction and access data to translate into the real address by looking at the translation table. Okay, translation table of the process will have the mapping to the real address. Okay. And this entry will say only kernel mode can read that real address, or user mode can read also. Okay, so you can see this table has a flag to indicate the access mode. So MMU will follow that because MMU is a hardware. If you want to access the kernel space, the MMU will trigger exception. Then your segmentation violation will happen. Okay, memory segment violation. In general, that's a name for segmentation violation. And then that is how the hardware triggers the runtime exception access violation. Okay, so this table is also in the kernel space, so it's cache 22. And then the mapping from the virtual space to the real address is through the building of this by OS. It has been built up. They will not overlap between processes, among processes. Okay, you will never get to kernel space either. So every process running its own translation table mapped to different places in the DRAM. Okay, in an actual place in the DRAM is different. Okay, so even though say they all have a main, and the main printed the same address, you can verify with your fellow students, and you can verify yourself by building several runtime. If they all start with a main, that in C programming, Java, and then you print the address on main, they are all the same. Everybody here, any program you program, it will print the same address, but they are virtual. They are mapped to the real addresses in different places. DRAM, okay, this is real. So the DRAM will have the actual location mapped by that virtual main. Okay? So every virtual main is mapped to a different place, even though they are called the same, even appear to be the same address virtually, but they are not really the same. Okay, like you're going to the kitchen of different houses, that doesn't mean that you will meet there. Okay, because it's different houses, they map to the real different space. Okay, but everybody's got a kitchen, everybody's got a bathroom, everybody's got a bed. So I'm in bed now. Are you in bed now? How come I don't see you? And of course you know. Okay. Yeah, does that make sense? So the translation table built during the creation of the process. We're going to try this build a translation table is the main thing in the phase 10. Okay, for the OS, for the process to run in several DRAM pages instead of in one 4K byte. Okay, this is several processes, each one is squeezed into the one real 4K byte. So all the addresses are real. That's a real mode, and it's not the virtual mode or multi-user mode or protected mode, people say. Okay, so we're going to do the construct like this one, the blue area. So the construct like this one is we're going to program MMU to use a table. When that process is about to load, we can program that. And it's on the fly, it's hardware on the fly. Whenever the CPU asks for fetching the first instruction in here, it's a virtual address, very big, like 500 meg. And the MMU will see the table mapping for that process, map to, you map to 14 meg, 15 meg, okay? It's not 500 meg. Another process also has the same 500 meg to start the first instruction. All that map to a different place in the DRAM. Okay, so that's on the fly. So this is not software. Okay, otherwise it will be too slow to run this program. And data access from the instruction also is going to be checked by MMU. So basically, CPU has no knowledge about real addresses. CPU are fed with virtual addresses, and every address outside of the front-side bus actually intercepted by the MMU. Okay, MMU will translate and give it a cache, the real address. Translation results is going to be given to the cache system. Okay? The cache system then check if the cache hit. If it not, if it is, then that will be great. If it not, then go to fetch it from the next level of cache. All these things you learn from the cache system. So MMU is going to result into the real address and give it to the cache through the lookup the translation table. Okay, so building on the translation becomes the key about the assignment phase 10. Okay, phase 10. Instead of squeezing the rounding processes in a 4K file, we can have several pages to map. Okay, to map the rounding process too. Okay, so that's the goal of the phase 10. All right. So goals in the previous OS phase, a new process can run within a confined 4K byte memory page. In this phase, the virtual space of 1 GB will be given. We can change this number to whatever we want. In 32-bit platform, the maximum is 4 GB. We just practice 1 GB virtual space for each process. So they all run in virtually the same range. Okay, and then that's from 500 meg. We're going to define a constant, so easier to program. This is the number hexadecimally. That's a VM star, virtual memory star for a process created by exec service. Okay. To byte the 1.5 gig minus 1 byte. So that's the virtual memory ends at the hex of 5 followed by 7x. So that is 1.5 gig minus 1. So that's exactly 1 GB. Number 2, virtual space is supported by real DRAM pages, but with only partially for the current runtime of the processes. So we're going to support just the portion that the process currently used. The hardware device that translates virtual addresses is the memory management unit. Each address the CPU uses to fetch either the instruction or access data is to be first translated by the MAU on the fly, because before giving that real address to the cache system to check whether it's a cache hit. Okay. Any questions? So next phase we don't get to do it because the page table I said at the beginning only a few pages, and then if a new page is asked by the runtime, that will trigger page fault because triggered by MAU because it's not present. Okay, not present page fault, and then that will go into the page fault handler. MAU will notify CPU to jump to by the IDT table. There's an entry that goes to the services. On the kernel, one of the services is page fault handler, not present page fault handler. We'll allocate another DRAM and furnish that missing entry that MAU saw, and then the process can resume from the same instruction, repeat the same instruction. So the program counter doesn't up-count IP in that sense. That's all done by hardware, okay? The program counter doesn't up-count. So the software of the services in the kernel is to fulfill that with a not present page fault handling service routine, okay, to allocate another new DRAM and then register into the table entries. And then that process will rerun, and then rerun this time it will be there, okay? So that's a not present page fault. Okay, so if you, so that's the idea. Okay, what that means that we can have the limited number of DRAM space to serve a larger virtual process space. Okay, and quite a few processes. Okay, and then only the most recently used DRAM locations are being furnished at that time. Does that make sense? All right. So the process created by the 6xx service will become virtual. The instruction on the process will start from 500 meg. Okay, that's the number. And the process stack will end at this 1.5. Okay, 1.5, 1 minus 1 gigabyte. All right. So you ready to see? Okay. So a process created, okay, and then the virtual space. Sometimes we say that's a virtual process, okay, and then the okay, so we're going to do the beginning like this. You say this is what? This is kind of like a processing 4K by expanding the virtual space, starting from 500 meg to the top 1.5 gig minus 1 byte. So that is the virtual space. Each unit here is 4K byte. Okay. So you say, why am I drawing this square bracket? So what we're gonna do is that we're going to use DRAM in the unit 4K byte as a one page. Okay. So the paging system is what we call. This is called a paging system. So we support virtual addresses by 4K bytes. Okay, by 4K bytes. Inside that 4K byte, the order didn't change. Okay, it's real. But okay, so that means we're going to have in the DRAM flying 2 4K byte pages to support that. This could be like in the hex E 03000. Just for example, okay. For example, the real address of these 2 4K byte pages, out of the 20 pages we have to play with, okay. And then the virtual, it looks like this. So this is the function starting point. Child stuff will start from here. Okay, we can say that's main, doesn't matter. So we know that's the beginning of the code right there. And we're going to have the traffic here. Okay, we're going to build the traffic here with the arguments inserted, okay, on top. So that the runtime, okay. Addresses are virtual. So what does that mean? That means the traffic IP points to 500 meg. Okay. Traffic EIP has this number, unreasonably large. Okay. Unless it's being translated, there's no way to get to the DRAM correctly. Okay. So the dotted lines to the translation table we're going to build with the 2 entries to translate these 2 pages into the 2 DRAM pages correctly. And you know that this traffic is going to be somewhere like 1.5 gig minus the size of the traffic minus 2 integers. Okay. So that is going to be close to near almost 1.5 gig. Okay. That is actually 1.5 gig minus the size of the traffic minus 2 more integers. Okay. Okay, more bytes. So that's where the traffic is gonna be. And that's put in the PCB. Okay, you say, what's this address? Where should we put in the PCB? Traffic pointer on that process. When we create that process, okay, we don't set a PCB like before, traffic address like before anymore. We set it with this constant. Okay, with this constant. All right. We can make a constant called this virtual memory traffic. Okay. Every process created from the exit service will have this constant. And the instruction is a VM start. Okay. Every process created by exit service will have this in the EIP of the traffic. Okay. So when this process starts to run, MAU needs to get ready using the right translation table to translate virtual addresses. Okay. All right. And the translation, okay, so virtual address translation. In exit service, the translation table, TT, the MAU needs will be created when the virtual process is selected to run and after creation, when this process is going to run, before the prompt loader, the MAU will be given the translation table by setting the MAU with the given TT. That's recording the PCB as we created, this TT in the exec service. Okay, I missed a parenthesis. And when the process ends, the MAU will return the original translation table to the OS translation table that the OS uses at the beginning. Okay, so we're going to get that OS translation table in the kernel initialization for the kernel data, and then we're going to change it back. Okay, we're going to redirect the MAU to the new table for that process. Every process has its own table, and so that's why it's recorded in the process selected to run, PCB. And then when it finishes running in the exit service and the wait child service, when we reclaim child process resources, we also reclaim the DRAM pages it has been using and change back the translation table. Okay, because the translation table is going to be nullified. Okay, by then. So MAU does not have translation table to use anymore because child process are gone. So is the translation table. So we switch the table back to the OS translation table at the end of the exit service and the wait child service. Number 5, the OS translation table is created during the OS push drive for the kernel to use. The first 4 entries of this table will be part of the newly created table for the virtual process in order to map to the area of the kernel services. That's kind of like we said the API call and the actual service code call. We know that when we copy the child stop here, we copy 4K5, and the API is close to here, and they are just by the current process IP offset plus or minus to get to the API call. The API call will have the crucial interrupt 128. When that happens, IDT table needs to be looked up, but CPU needs to know where the IDT is. Okay, CPU will need the IDT to be still there. So basically, this is a mapping to the kernel space. People say, so what does that mean? That means the user process space is not really 4 GB. Okay, even though we want to colloquially say that, but we got to reserve the bottom portion. Okay, every OS is a little bit different. At least a certain range, like 16 megabytes, in order to do what? In order to map to the kernel space. So that's the kernel space is here. Okay. In order to get to kernel space, we got to copy the first 4 entries that can point to the kernel space from the kernel's own OSTT. Okay. So OSTT can translate the address that the interrupt 128 wants to go to. Okay, this V will jump to according to the IDT. We know the IDT is here. If we cannot get to IDT, the target PC will reboot. Okay, we'll have to reboot. So there's the 4 entries in OSTT, can point you here. Okay, I will explain further about this. So this is why we say, the process runtime actually has a mapping virtually to the kernel space, which is true. Okay, and that's the uniform kernel space, kind of like a runtime library. It has to be there. Okay, so the process runtime needs that. But we know that user mode, kernel mode switching in the interrupt 128 circuit will make that happen, and then the IDT table can be accessed to read by the CPU. Okay, because that's the design of the interrupt gate, interrupt call. Okay, so that's what it means. Okay, so let's see the virtual address translation. We target on the Intel platform. There's the Intel Pentium 2 400 MHz in the target PC in the lab. Even though that it runs DOS, but it has the capacity to do the virtual space. And then we're going to do that ourselves, even though the DOS doesn't do that. virtual space translation, the Intel MAU uses a two-tier translation procedure. Okay, so let's get into the detail about the translation. Right now we cannot say, oh, every process has a table. I cannot lie that there to simplify things. It's actually a two-tier table system. Okay, two-tier table system. So I'm going to erase this. So this is the DRAM, okay, not too many pages. And this is the one process virtual space. Only one process virtual space. Okay. Every process has the same virtual space. Starting from the bottom here, and then the mapping 16 meg. Okay, 0 through 16 meg minus 1 byte. And then followed by this side we actually don't use. And when we start the user process here, okay, and ends here. Ends here, okay. VM. And we also have a constant near the VNN, that's the traffic address, virtually put into the PCB. Okay. We can freely set the process virtual space all the way down to 16 meg to start, okay? 16 meg to start. And then all the way up to 4 gig of minus 1 byte. 4 gig minus 1 byte, okay? And that's a maximum virtual space, okay? It's 4 gig minus 16 meg, okay? In 32-bit platform. Okay. All right, I'll just start a new story about the details about the Intel MAU. The Intel MAU, how is it designed to translate things and why. Okay, so that's a virtual space, okay, a virtual address. A 32-bit virtual address. It's going to be separated into 3 parts. Okay, 3 parts. And then the first 10 bits, followed by second 10 bits, and then the rest of 12 bits. The first 10 bits is going to use as the entry number to the translation table. And this is the main translation table. Okay. So we're going to have a main translation table, kind of say main, main translation table, and then must be sub. Yeah, they are sub. And each entry can have an address of a sub table, okay, of one sub table. That means the beginning address, okay. In the entries, all real addresses, okay. And then this is the sub table, a sub table. And you'll see the reason why main and sub tables happens. Okay. And what that means that how many entry here can have how many sub tables? Okay. Sub tables. All right. So there's a main table, one main table. We call it TT, and then there are sub tables pointed to by the entries in the main table. Pointed to meaning that the first byte address, real address, okay, of that table. Table could be more than 1 byte in size. Okay, the tables are actually in 4K byte sizes themselves. Okay, each one is 4K byte. So nicely to follow the DRAM page unit. Okay, that's what everybody does now these days. All right, so that's the. All right, so this one will point to another one, etc. Okay, so you can see, and then all these can point to so many different subtables. Okay. In the end, they are 1024 entries. Okay, 1024 entries. So that means each entry is 4 bytes. Okay, 4K byte. We have organized this into 1024 entries. Each entry is 4 bytes. Okay, so each entry is 4 bytes. Like that. Okay, same as the subtable. Okay, and then the subtable have the same construct, same meaning. Every entry has a real address to a 4K byte page. Okay, 4K byte page. Okay, I just use blue for 4K byte pages. So each subtable can point to 1024 different 4K byte pages. Point to meaning bearing the real byte address, starting of the starting byte of the 4K byte area. Okay. So you can see the expansion of this becomes huge. Okay. So this is the last, and last subtable can also do the same, point to 1024 4K byte pages. Okay. So in between, also many 4K byte pages from other subtables. Okay. So that's a maximum usage of the total 4 gigabyte space. 4 gigabyte space. You can calculate. So this is each one is a 4K byte DRAM pages, and these actually contains the instruction code data. Okay, before we didn't have to waste DRAMs for tables. We just squeeze everything into 4K file, yeah. But it may not be larger enough, of course. That's the first reaction you have. So we're going to provide multiple pages. And while doing that, we can expand into the table translation into the virtual space. So the virtual space can be a maximum 4 gigabyte in a 32-bit address platform. Okay. So the user process can be set to roam about 4 gigabyte. 4 gigabyte over 4K byte. How many pages? If the process use all the total 4 gigabytes, have you tried that? you declare 3-dimensional floating point arrays for graphic processing. Each dimension is 1 million points. You're going to overwhelm Titan Athena. Okay. So you probably don't want to do that. It will probably let your program runs. But if you really use those points for the IJK loop, you will see it's really slow. It's going to be swapping into the disks because DRAM may not be that big for each process. The limit that the administrator set, as you at the shell prompt, you type limit, enter, you will see you are limited to the total runtime of 8 megabytes. Okay, so after 8 megabytes of DRAM, that is, the pages are being swapped out. Okay, the 4K byte DRAM here will be swapped out. They are virtually there, mapped by the tables, but they are not currently in the DRAM. They are in the swap space. To support the DRAM, the OS virtual memory is using the terabyte swap space. Partition. Okay. So that's the thing of the process images are swapped out here, and they are swapped in when they are needed. Okay. And they are swap in, swap out. So this is the swap. Okay. So you can see that's from the system platform's viewpoint, the virtual space, meaning the swap partition, how big is that? That's the natural extension of the DRAM. The DRAM may have only 2 gigabytes, okay? And then you know that one virtual process is already over 2 gigabytes if it wants, okay? And then of course, the OS must consider there are hundreds of processes running once you turn on your laptop, you know, and I have 300 processes running, you know, and then once I turn on my laptop, there's no way that everybody is going to use the gigabytes. Everybody is going to use a few 4K bytes, and others are swapped out. Okay, this is not the lock-in disk home directory. Okay, That's the, not in the file system, user file system.
I checked my thing, and there is no limit on the size of the processes with virtual memory.
Yeah, this is just it's defined in the stack size.
Stack size, that's different from virtual memory.
Yeah.
Yeah, stack size is limited to like 10 megabytes.
Yeah, so that will eventually become the limit. So virtual memory.
Well, if you allocate all your memory in the heap, then you don't have that problem.
Yeah, the code is not that big. The code is read only. So the code will allow you as big as you want, but the runtime stack is limited.
But the heap
is continued from the runtime stack down.
The heap is unlimited.
Yeah, the heap
The
is.
heap doesn't count in the stack size limit.
It doesn't say heap. It's actually in the Linux convention. It's the same place.
The stack size limit is how far it's willing to grow the stack segment, but you can allocate as many heap pages as you want.
Yeah, heap is not in the hardware. Heap is a OS construct. So that the heap is the global data above. So the global data, your code, global data, and the constant, and the heap starting from here. Heap is a runtime construct when you do the new and memory allocation. So it's actually continuous in the virtual space that the stack comes down, the heap grows. So that they all share this space.
Yeah, the stack limit is how far the kernel is willing to grow the allocation for the stack, though.
The allocation is a service. Yeah, the heap is a service. That the usage of this depends on the code. The stack is the runtime instruction.
Yeah.
Compiler.
Well, the kernel starts with allocating 4 kilobytes for the stack, I think, and then when it tries to use more, it'll expand that automatically.
Yeah, they interchange this space. So the pointer is allocated, is kept in the OS for the heap pointer. So that can have a list of the allocation in segments. So there will be a compression in order to make it to squeeze the segments. So there will be segmentation by every time you do the memory allocation. So that's done by the OS. So the heap is not the. So what that means that the limit is the stack is covering the heap. If you don't use heap, then you have a 8 megabyte of the total DRAM.
You have, I think, a lot more than 8 megabytes, because the heap is not included in the stack limit.
Again, the heap is not the real construct. Heap is the OS kept pointer whenever you do a service call. That's still using the same space of totally.
It's not the limit is not. It's not a limit on the size of the space that has the stack or heap. It's a limit on the stack allocation that's managed for you.
Yeah, so that's why it says, but it's actually the same thing. The total DRAM that the process can use in this area.
No, it's just the stack limits. The process can use up to like pretty much the full 4 gigs of RAM, but only the stack is.
Yeah, virtually. 32-bit. Yeah, but if it's 64-bit platform, it's bigger than 4. Yeah, so that's the. But the limit of the DRAM that you can use here before swapping out is I believe that limit says 8 megabytes. The virtual space
that would be pretty slow because there are plenty of programs that need to be using more than 8 megabytes of memory.
They are not all the time in here at the same time. They are swap out, swap in. Okay, so maybe there's a heap size that's not defined. It's a global heap that the system admin can have for each process.
The heap is defined, at least on Linux, by mmap calls that allocates pages.
Yeah, it's a break service. So that's counted as a virtual space. So this is a virtual space, right? And then virtual space always has a contiguous the process space. And then we know the construct is that the heat goes up in the virtual space, stack comes down. So, but that limit is saying the CPU time and the actual stack size in DRAM. That's a generic term. Yeah, that's the limit of the total of the real DRAM pages a virtual process uses.
So a process can only have 8 megabytes of physical memory at one time.
Simultaneously.
I don't know if I believe that, because there are processes, there are programs that are going to want to use a lot more memory than that.
Yeah, but that's virtual. It's called
But if
swap.
you have to be swapping all the time, that's really slow.
Disk cache, yeah. It's a speed up through disk caching. Disk caching is actually also DRAM space that forms into the actual swap. So there are all the optimization technology ease out the your feeling about it's not that slow. Maybe different OS constructs are slightly different. These days they all have the optimization alternative to set up as a system admin. Okay, so that those parameters can be overwritten too. There are other tables to overwrite that the user limit.
Yeah, you can change it all.
And they can be altered with another table. That's
I think the real reason for the stack limit is once the kernel, on Linux at least, once the kernel grows the stack, it can't shrink the stack again. Just because of the way it does the stack growing. So the stack limit is to make sure that you don't have you don't have like a gigabyte of stack and then not much space left for the heap.
yeah, that's true. But that's virtual space, right?
Mm-hmm.
Virtual space is not limited.
Yeah, I'm thinking in virtual space.
Virtual space is your pointer is legal to set to this address.
Yeah.
Then you can read that. You are allowed to read that. But whether it's currently in the DRAM is another, that needs to be verified. Okay, well, I'm just talking about fundamental ideas. Okay, it's not really the final optimized version of the current modern OSs. So you may need to find out the real actual config construct could be slightly different. Okay. All right. So so there are 1 megabyte. Okay, 1 mega pages here. Okay. So if all the DRAMs are needed, there will be 1 mega pages. So the purpose of this is to have a sparse distribution in the entries, so that most processors will not use all the entries here. Okay. You see, 1 subtable entry is 4K byte. The whole subtable is 1024 4K byte. That's a 4 megabyte. Okay. It allocates 4 megabyte because 1024 4K byte pages can be pointed to by the 1024 entries in the subtable. So how many subtables here? 1024 subtables. So the entropy is still the same. That means it's a 4 gigabyte because the 4K byte DRAM pages times the 1024 is 1 subtable. And then we know that there can be 1024 subtables. So basically it's still the same, to the 10. So it's still 2 to 30 seconds. Okay. So so that's still the total addressing by bytes. So nothing changed. But the thing changed is we're going to have virtual address translation, and we're going to use, and most processors only use a few entries. Don't need to use all the entries. If we have 1 big table, this 1 big table to address all the necessary pages, then we're going to combine this table. The table will be 1 mega. Okay, 1 mega entries, because they can be 1 mega DRAM pages need to be pointed to by 1 big table, 1 big TT, One big TT, that means that that TT needs to have 1 meg entries, okay, 1 meg entries. And when one big table has 1 meg entries, each entry is 4 bytes, that's a 4 meg. So one table is 4 meg. These days 4 meg is nothing, but when we started the Linux system, there's no way, Unix system, there's no way that you can have each process having the 4 meg table. Because that table cannot be swapped out. Okay? The problem with this table is that they cannot be swapped out from DRAM. Okay. So what happened is that when you have 100 processes concurrently running, each one needs a 4 meg table space already run out of gigabytes. Already half a gigabyte there. So there's no, not enough DRAM at that time. Right now it doesn't seem to be much. Okay. But the big revolution is coming. Okay. When coming, we're going to have 4 mega instead of 4K byte DRAM pages. There will be 4 meg paging system. Okay, 4 meg paging system that will ease up probably some of the 2-tier translation into one question.
So, in this particular instance, it's like the page size is pretty much standard at 4 kilobytes. And you translate that to a 64-bit system, you just have more translation tables, correct? Like you have another 1024 entries and another 1024 until you get to 64, basically.
Yeah, I'm not sure if we do have a true 64-bit translation system. And
because the translation table is similar to the 32-bit one until you get to that point, and then it branches off into different things.
Yeah. Probably only in the 4 megabyte DRAM construction can we really reach the 64-bit of the process virtual space. Because right now the hardware only up to 2 to the 52nd byte. I think that's the 4 terabytes.
Virtual memory.
4 petabytes. 4 petabytes. Yeah. The hardware in the circuit that can accommodate. That's the address bus. 4 terabytes of DRAM. So the virtual address is 64-bit, actually mapped into the maximum DRAM sizes. So the table entries are empty. Okay. Well, anyway, let's first talk about this. Okay. So each entry in the main table can be the place to find 1 4 megabyte location. 1 4 megabyte location. Okay. This is also the reason why we want to copy the first 4 entries. The first 4 entries are copied from the OS because the OS use that to point to 4 subtables. Okay, 4 subtables. And each subtable is responsible for 4 megabytes. So total is 16 megabytes DRAM access. So that can cover the MyOS.CLI up to 14 meg. Okay, so the primary reason for Intel you to use a 2-tier memory translation is because the savings of DRAM. Okay, saving of DRAM. Again, if you have only one table, this table is 1 mega entry. Okay. You seem to be lost. All right. So if you think about what I originally said, there's only one table for one process to translate 32-bit address into that table. Needs to have 1 meg entries to map to 1 meg DRAM pages. Okay, so it's not done like that. It's done by 2 tiers: main table, subtables. They don't need to totally exist, the subtables. So we have a savings of subtables. Okay. The main table only needs to have few entries active, valid. Okay. Only use a few entries. because one entry can be responsible for 4 main. One entry is to a start table. Yeah. One start table exists, that start table can map to 1024 4K bytes. Okay? So because most processes are not that big in code, okay, in runtime stack, in the heap, they don't need that many bytes, that many 4K byte pages. Okay. Okay, I'm sorry, the story is very long. I cannot treat it in 140 words. Or 280 now. Alright. Okay, so this first 10 bit is used as the entry number to the main table. The second 10 bit is used to address into the sub table. The last 12 bits didn't change. Okay. So inside the 4K byte, we have allocated from the sub table. The last 12 bit in the virtual address is the same as the location inside the 4K byte. To address 1 byte, you need 12 bits. Okay. So that's why it looks like that. All right. And then the savings of the 12 bits is that we can save the 12 bits. We don't need that when we do the translation. So what that means, the MAU doesn't translate that. MAU translate the first and second 10 bits into the page numbers. That's the virtual part. Okay. And in that entry is the real address of 4K byte. Okay. I don't know if I should just do without the projector. I'll just continue here. Okay. I will continue with the whiteboard thing next time. I'll try to complete this. There's a reading comprehension here. Okay, two-tier translation, okay, looks like that. And then all right. So first 10, second 10, and the last 12 bits into the DRAM pages. Okay, so basically it's a page number mapping, 20-bit mapping to a different DRAM page, first 20 bit. The PCD will need so data structure in the process, PCD will need to have a TD. So every process has a different TD. Okay. So that is the main translation table address in the DRAM. And then the page 5. Okay, we're going to have 5 pages to start. We're going to have 3 table pages and 2 for the instruction and stack. So we need 5 pages. So we need to record the 5-page usage, the 5-page number instead of 1 in the previous space. Okay. So the PCB is now null. The TT in the PCB is now null. Then before the prompt loader, we should call the CSC159. Okay, CSC159 with this TT. So that we can proceed with prompt loader, because the translation needs to start in the prompt loader, since the prompt loader will be given a very big number that is the constant of the BN traffic. Okay. BN traffic. This is 1.5 gig minus the size of traffic minus 2 integers.
So like the actual size of 2.
Yeah, the 2 integer space. The valid entry in the main table is set with the real address of a subtable, which occupies the whole DRAM page, because one subtable is 4K byte. And a valid entry in the subtable is, by the same token, set with the real address of a DRAM page. That DRAM page is used to carry the instruction or stack. Entries not yet set that are invalid. And the MNU will issue a not present page default CPU exception. But we don't do this in this case. Only when the code changes to trigger the page fault will this happen. Therefore, there are flags like valid in each entry of the table to set as table is created. More setting flags below. The exit service will start by allocating 5, not 1 anymore, DRAM pages to create a main address translation table, TT. 1 instruction table, that's a subtable. 1 stack table, that's another subtable. We call them instruction subtable or stack subtable. 1 instruction page. Okay, so this instruction table will have 1 entry point to this instruction page. Same as this stack table will have 1 entry point to this stack page. So altogether, you can see there are 5 of them: TT, IT, ST, IP, SP. Okay. A table has 24 entries, and each entry is 4 bytes in length. So a table is 4K byte to fit into 1 DRAM page. 2 entries in TT point to IT and ST. Okay, so 2 main table entries point to 2 subtables. Since the virtual space starts at 0.5 gigabyte and its first 10 bits, the first 10 bit read by the MAU will be this number, the first 10 bit binary, and this is 128. So that will be the entry number in the TT. Entry 128 needs to be filled in the address of the IT instruction table. Okay, so that's where the IT address is in the entry 128 of the main table TT. And the next 10 bits of the virtual address is those zeros. So what that means is that entry 0 in the subtable IT instruction table will have the entry of the IP instruction page. Okay? And the rest 12 bits of the 0.5 gig is 0 into this IP to get the first instruction at the location 0 in the IP instruction page. Number 6, the processor argument and the traffic will be created at the end of the virtual space. So that's the virtually towards the end, stopping the end, in which the first 10 bit is this, okay, and that is 383. 383 is the entry number of in the TT for address of ST, and the second 10 bit is this guy. It's all ones. Okay, here we have 10 bit all ones, and then is the entry of a stack table. So that is 1023. 10 ones is 1023. Decimal. Okay, so entry 1023 in the subtable stack table will hold the address of the stack page. Okay, and then the rest of 12 bits is the to fetch data. Okay, for the stack page into it to fetch data. The beginning 4 entries of the OSTT will be copied to build the new TT. Okay, so the initialization we can get that. Get CR3 call, we'll get that. Okay, get the OSTT, and the EIP is going to be set to the VN start half a gig, and the PCB traffic will set to the VN end minus the size of the traffic and 2 integers, the size of 2 integers. Okay, for argument and the returning address. We can set a constant in the constant .h using the VN end. VN end minus size of -2 and then +1. Okay. Because this one is already -1, 1.5 gig minus 1. Difference between 1 bytes. Okay, I think I only have time for that much today. Okay, so next time we'll continue from here. Yeah, let me know if you have any questions. Especially the previous page, you got to get it right. I'm grading it. Tonight I should be able to finish that. If it's something like a integer array, size of the array, size of this array, some people, one team write like this. So basically the target is signal table. I haven't verified this, but you can write it and verify this. You can print it. Yeah, you can print it. I think it will work. The compiler will look at the actual data. So basically, we can write a test code. Local variable.
Don't you know, get the size of the first dimension now? Right.
You always use a second line. It's gonna get complicated. You always have this like this one. Okay, so that's the size out. 800. Wow, that's correct. What? It's not quite what you expected. It's 64-bit. Okay, 64-bit. So 10 times 20 is 200. For them, 800. So that's integer. Okay, integer. You said what about long? 1600 because it's 32-bit. Okay. How about long? That's not a pianist. so basically, it's the long is prepared for next one again. 128-bit compiler. So yeah, nicely, it's still the 4-bit for us on ATOS, okay. And GCC, the default is 64-bit compiler. If you type M32, mode 32, okay. So that's 32-bit mode. In this case, there's no difference. And then unless you do long, okay. And then when you do long, you say still 800. So because it's 32-bit, okay. If it's the default is 64, or you said -M64, okay? And because the default is 64, and that's 1600. But if you want to specify type, like we usually say, it's not the name, okay? It's when you program it should be the type. So you just need to erase this thing. And that's the type, that's the size. Okay. The whole thing. The whole thing. Alright, so that's the size. And then of course you don't need that many space, or even without space. But if you loop, okay, of course we change this to prod num with the signal. This is the function pointer. And so the type and the first dimension, second dimension, the second dimension signal, okay, the 32, 20 times 32. If you loop on this guy, okay, then it's just the size size of the rest, the in 20. Okay, that's the second dimension. Or use constant. Does that make sense? So it's not the size of signal. So it says as opposed to I think only two teams are, or three teams, you know. Two teams use loops. And 14, I think 14. One team named the name, and then the two teams use loop. Okay, so you can see the code here. So I grabbed all the signal table keyword from all the kernel.c and then filter with another grep of B0. So I gauge you like here, my B0, operate on signal table. It's optional. Since it's a name of an array, ampersand optional. Size of function pointer type. So this is the multiplied by the content, and that's good. And typically when you have an array, you know it's contiguous in memory, so we can specify like this, in this case, like in 10, 20. So the array in one dimensional is consecutive, one after another. In two dimensional is organized as a second dimension group. And the second dimension group, 20 here, 20 here, 20 here. So this is local variable, local array, the memory from low to high. Okay. So that's the 0 here. Okay. First dimension 0. And then followed by the next one, 1. And the last two, 18, 19. Okay. 18, 19. Group. Each one is 20. The memory allocation becomes like segmented like this. So that's the okay. So that's the how the array is arranged. If you have individual function pointers as signals, then you may have something that looks like this guy. Okay. So this that means it may not be an array that you have B0 in the file. So they shouldn't be in the same address. And it will work if you declare them globally, like our signal table. So if you declare them as a function pointer, so I got lots of signals, signal 0, signal 1, without using array for some reason. So that is that is continuous, you know, because they are declared continuous. So this will be the first, followed by this one in the memory. So you can do that, but then you don't have an array thing. If that's just an example. If I had 20 signals here, okay, you have 20 signals. But if you have 20 times 32. You may also name variable like 0, 1, 0, 0, 0, 1, 0, 2, all the way to 0, 19, and then continue with the signal 1, 0, 1, 1, 1, 2, all the way to signal 119, 119. Okay. The names don't really matter anymore since they are consecutive. So in this case, we usually use an array, okay? And two-dimensional array will fit the bill because you're going to have 20 of this, and each one is going to have all the way to 31. Signal 0, 31. Signal 1, 31. All right, so that will take all day just to declare 20 by 32 signal names. So we use an array. So that semantically, you should learn how to use something like this in the CSUS to show that you know how to program C. Okay. B0, what that means. If you have a loop, like I said, you loop the first dimension, the second dimension becomes the size of the function pointer with the bracket 32. And that comes from sig_num. Use the constant name, of course. If you loop both dimensions, typically that's how you learn initialize a two-dimensional array in CSC10, and then CSC15 if you never gone into array in CSC10. So you have IJ loop. One thing has IJ loop, which is fine, and then the size of function pointer, just a single function pointer. Okay, that's the address. Right. So that's it. So I may not grab the loop, but this is some of this may be inside the loop. I just grab one line where there might be zero call occurred. Okay, so see, this is using the name signal table, and then the experiment tells us that that will work too. And then and this is definitely not right. Prod num is a constant, and that means it's a literal number. During compilation, this will be replaced by the 20, literally. 20 as an integer literal, that means 32-bit number. Okay, it's 32-bit. So you B0 only 32-bit. That will be just the first function pointer in the first process, the first signal number 0. Okay. And this is not right either. So all these are not right. Okay, so this one's better. So this has a 32 signal function pointer, 32 function pointer. If this is in a loop, second dimension will be erased like this. So you still have to have first dimension to loop through the PID. This is just one function pointer, so just 4 bytes and 32-bit address. Okay, so that's so this is the same thing like we did in the early phase 1. B0 acute, and some people just use the prod num as a size of, but it's not right. Okay. Okay, so that's the thing. One thing had this problem that it works, but it actually worked only in this case. Oh, by the way, you don't want to use ouch in the service code, okay? And you say that works, but that only works for this case. It's kind of like you have a method that receives the integer x. Because we're going to test x with 5 from the caller, then you say, I will print x. Why don't I just print 5? Okay. The purpose of this is to send whatever x to print that x. But you say, since we only have ouch to test, Control-C, sig_int in this phase, so the service just directly use ouch. Okay. So now we're going to put the ouch in the signal table. Okay, signal table for that process. Then you can, some people probably program. The process is gonna be number 1. So I just program 1 here. No, it's gotta be the run pit, okay, the run pit calling the signal service with the pointer. So the syscall pass along without knowing what, but it's going to pass along 2 things. One is the signal number, okay, signal number. Don't know which one. It could be sig_child, it could be ouch for Control-C. So signal number, we have 2 cases to test, phase 6 and 7. One is the sig_int that we're testing. The other one is the sig_child. Okay. And then so that is the second dimension. Okay, so we have 32 different signals. This is number 2, and this is number. Okay, So you can put in the ouch function pointer, okay? Function pointer type. So the syscall pass along this and this. And then the service does not know what they actually are, okay? So you cannot hardcode ouch there, just like you write a method print x, you cannot say print 5, okay? And if you write something like if x equal 5, print 5. And then if x equal something else, print 6. But you say we only test 5 and 6 in the academic work anyway. so you know that it's gonna print either 5 or 6. But okay, so that's the thing, we don't know what function pointer that is. If we change it to ouch2, then what you're gonna do? Change the kernel code. You cannot change kernel code. It's the caller user process provide whatever that name the user process may want to call. Okay, so this is not fixed. Something inside here is the user process. You gotta consider different names, okay, different situations. I'm just provide that for you to not spending too much time to figure out how to code user process. So I provide an ouch function. It can be called any name. Okay. Yeah, and then it happens to work. One team has this setting, happen to work accidentally. Okay, I don't know if it's good or bad. It's the traffic is moved down. We're going to put that's the alteration of the ouch, handler phase 6. So this is the ouch address. Okay, in service code we do not know. We just know that it was registered in the signal table for the process released upon Control C that was waiting for keyboard input. It could be PID1, PID2. If you push N key twice at the beginning, there are two user parent processes that are using terminal 1 and 2. It could be PID1 and 2. But it's released right now, depends on which terminal you hit Control C. And then it has registered the SIG-in function pointer. Previously put some function pointer. We know it's ouch in the proc.c we use. It could be different name. So that's called by the syscall signal. Syscall signal. Syscall is the signal call with the SIG-in given. So that's commonly known constant. And that's included in the C code, if you program C code of ATOS, that's include signal.h. So that defines these constants. So user process can include them. You can use it. Include this prototype, include this constant. So we put the ouch here, the user process, that is the user request. Okay. So that's where the signal table register is a function pointer. And there are 20 times 32 function pointers. Maximum can be putting in there. But you got to zero them first. If you don't zero them, they will be misconstrued as there is a registration when you hit Control C here. But it actually never registered. They will jump to whatever that address is to execute instruction. It's going to call save all. Okay. All right, so this is ouch, and then this is the original returning point. Okay, so that's from the original traffic that before we move. So we move down to do this, and that's what we want to do. But it will also work if you happen to use the EBP inside here. But the EBP inside here is the resuming EBP, okay? You say EBP -8. EBP was in the runtime stack like this here, okay. And then EBP minus A happen to be this guy. Okay, minus 12 happen to be this guy. So you use the traffic EBP address minus A minus 12 to set these two things. So that happen to be the same place. Strangely enough. You know why? Because this is the result. This is when this, at this point, is a read surface. So that the process waits. So we control C and alter is runtime stack. Okay? So this is when the says read, calling with dot, 3 arguments. And inside the says read, right at the point of interrupt 128. All right. So this is the stack right now. And then we release that waiting process when we hit Control C from the wait queue of the keyboard wait queue in the terminal data structure, right, in the KB service. So that is what the state of the EBP right now. Okay. The state of EBP right now, in another way to say it, there's nothing stacked, nothing here. So since it's nothing here, minus 8. Why would it be minus 8? There's a return address. Okay, so we have return address. When this is called, okay, this is being called, they will be in the stack here, and then push the original EBP. That's a user process EBP, okay, in the user proc. When the user proc call says read, okay, when the user proc call says read will have a code to push EBP, and then establish the EBP. Push this, and establish the EBP right here. Okay, EBP, and stack pointer is right now here. That's why we pushed it here. Okay, stack pointer was way out there in the user proc, but when the user will call the syscall read. Okay, and then the return address will be pushed here. And the code inside the sysread will start to enter. Okay, it will push the EBP. Okay, so that is the push it here. Okay, that's the user proc runtime EBP pushed it here, and then it's changed the EBP to the stack pointer, and then they are both here. They are both here. The return value. Yeah. Was it not minus 4, minus 8?
It's minus 8, minus 12.
Yeah, minus 8, minus 12. So that is the wrong place. It's not the right place. You come down from where the EBP points to, in the sysread. In the sysread, the arguments, 3 arguments on top. Okay. EBP plus 4, 8, 12. Okay. So the 3 argument is actually over here. Okay. The file number, first argument, first string, and then the length. So these 3 arguments, when the EBP plus toward high memory plus 8, plus 4. Okay. EBP will be now plus 4. Should be plus 4. Okay, that's call half of EBP. starts from there. Okay. Unless there's a push return value by default. Where the track frame is pushed. That pointer move down, push, move down, push. Move down. Minus 8, minus 12. Yeah, there's one more thing here. I think there's a default return void and null. It is null return. It was saved one slot. Check this. The function return. Okay. So, but if you alter this guy with something in the stack, the whole sequence is not right. I comment that if you add the
Local variables.
if you add something local, X, Y, Z, okay, and then you start a regular thing, even though this compiler will give you a warning not yet, and then you can continue to do SN here. So this will have to have the 3 slots, and then the minus A will come down to here, yeah. And minus 12 will change the Y and Z, okay. Change this is X, Y, Z. Declare the locally total low address. So if you add a statement here, okay, if you print Y, Z, print X, Y, Z, you will see Y, Z are being changed. Okay, if you initialize them 0, and that is the BP lower is not the right address. Although it's a good idea, to use the BP, but we don't know how many local variables there are to really get to beyond the local variable.
Could I use the,
Some syscall do have the PID to return, so it's not uniform.
what the stack point is that?
Stack pointer, yeah. So you got to do it like not using the content in the track frame, which is pointed to there. You got to do it with the pointer. How do you set a pointer? Just like I said, many people did. Almost all the team down the right. Yours also worked,
Yeah,
but it happened to be working this way,
yeah.
only for this. Yeah. So you can have a integer pointer Q, because P we use in the service, wrapper service, which point to ouch. And then and you set the Q to be the original track frame. Some people are very smart. Some people use the address of the current track frame, the last one on top. Okay, last one on top is the E flags. So it's the address of E flags, and that track frame points to. Okay, so that's the PCB or the PID that's being altered. Control C occurred. Signal table on the PID is not null. Okay, and then we send to the wrapper service to use that PID to find the track frame to alter. So the track frame pointer here has this E flag. All right, so this is the value if you don't have ampersand. But if you have ampersand, that means this are the precedence of the C syntax with the arrow and dot. Okay. If you're not sure, then you can parentheses around this one. So meaning that this guy, the whole thing is one item, which is the last one. That is the address of that. Well, you don't need to, okay. So the address of that becomes where we want to put put that thing. Now this is the original EFL. And this means the CS, and then the EIP. So you can do that, okay? And so you dereference Q with the P, okay? The P passed over to the surface is the arch address function pointer to the wrapper surface, so the int header, because this is an integer. Okay? Q is int star, okay? If you cover Q. Star Q is integer, if you cover star Q, okay? All right, so all right, so but you gotta do this right, because why? Because you're going to overwrite now the old traffic. You're gonna copy the traffic first into a temporary one. So you can declare traffic type, many people did, copy from the current one. You reference the pointer in the PCB of the process that is being altered right now. You don't need to amend CPY, you can actually equal, because they are the same type, the left side, right side. Okay, you declare local one, and the reference means that using the pointer point to that, while you point to the traffic structure, so that's the same type, okay? You don't need to amend CPY. You do amend CPY, people think, wow, you are really hardcore. That's an equal sign that you can use. That's from the original programming. You have integer x and y, then you know that at the same time you can x equal y. But you choose not to. You want to write my own main CPY for that, which is also good. Okay, if you have this in CSC159, you're not using Java, you're using C. You don't use equal sign. You use my main CPY, or just call the main CPY from the CPU C library runtime, and that will be okay too. And then that's a void pointer. Okay, void pointer type of the y x destination, and then the void pointer cast of the y ampersand y. All right, so that's copy. Okay, that's copy. All right, so you use copy everywhere. Then you start wondering, what's this for? All right, so that's a method. Okay, in Java, that's a method. So we have a contradictory thing going on when we learn the programming with a plus sign, equal sign. These are actually methods, which is true. So Java is that when you declare the x, x has many things. Maybe x has plus, x has a method for subtract, x has a maximum, x has a minimum, and then you all build into object. Okay. So then the old way of writing program in a simple algebraic notation don't seem to fit into object-oriented syntax. But that's the
In C++, you can define your own behaviors.
That's something that computer science people will think about. In fact, how did the language becomes like this? All kind of little confusing now. Right. But C++ is not really true. It's still comparing to C first, even though it let you have these fancy syntax, but it actually first rearranged back to the old C and by the GCC compiler. Okay, anyway. All right, so that's the. Any questions? Most CP students don't really care. It's just So long it works, it's fine, you know. What's the difference between using plus sign or equal sign versus a method?
There isn't.
It's $2 a day. Depends the code is a little bigger. All right, so that's the size of is a compiler time number. It's not a function. It's not a method. Okay. So this has to be found out the actual number during the compile time. So this will become the actual number. Okay, basically the code is doing this. The compiler will find out the size, okay, and replace it with this. So it's a macro.
It's based on the architecture, correct, too? Like if it's 32 versus 64.
Yeah, you can print all the size off and then verify them. Yeah, verify them. Yeah. So what does that mean? Is it has to be a known fact at the compiler time. So what does that mean? Is that you can, if you do things like this, so there's no such a syntax that it declare array x and y, right? So that syntax is not right. Even though you say the x is 5, y is 8, but still the compiler won't do it. Okay, you know, those are variables. And then when you apply to size, then there's no way to tell what size that is either. Okay. The allocation is gotta be a fixed one, literally fixed one.
What if you do like,
Memory allocation.
this is just a question, if you do constant x and y, as long as they're not changeable, correct?
Constant is it's okay. It's just a substitution, apply number, so they are known numbers.
So if they're not numbers that don't change at compile time, you can't use them.
Yeah, I think so. Unless you change a new C, make a new language, new C. But that will be more like interpreter doing the runtime can be.
Well, that's why you can do like preprocessor statements that allow you to put macros in for array sizes like pound define, constant, stuff like that.
Right. So we have the one macro we can practice a bit, you know. I have a hard time to decide where to put that macro. Is it a constant? Is it a method? Is it a tool? Right? So, you know, the last one here. Okay. I'll raise this window. So this is, wait a minute, what is this thing? This is not, this one here. Calculate the address, okay? Calculate the address, and that becomes a macro. So I just use this whenever I need an address. Some people use it like a method, that's fine too. You know, declare another integer x, we see x equals this. I mean y equals this. But the x is uppercase here anyway, so. And it will be replaced during the runtime as a macro. So this is not really a constant. This depends on the input x, right? Depends on the input x. So, so how does compiler actually compile this type of thing? Does it produce a lot of tables that x is 0, x is 1, x minus 1, x minus 2 to look up? Okay. All right, so this has got to be a runtime method, okay? Even though it's a macro, it looks like it's a defined constant, but this x is not known. So it's going to replace your code, except this one it won't replace. Okay? This one it will insert a temporary variable in the compiler. It will introduce a temper in the compiler. And so that is going to be linked that whenever your statement calls for the macro, the temp will equal that number. And then right?
The compiler just makes temp like an empty.
Yeah, I think it's an address,
Yeah,
right?
it's an empty address.
It's an address, yeah. Right.
And its content area is empty at pre-compile, and then whenever you call that inline function,
Right.
it will fill it'll fill that address as
Right.
content with whatever you call it with.
Yeah, it was definitely an address for it.
It's a macro address, though, right? So like, it's gonna be some reference or relative address to whatever the program is.
Right. So that's something I forgot about what I wanted to say. But anyway, so you get the idea. All right, and when you have multi-lines, so sometimes you have multi-line, you can write it like this, okay? Where the backslash, that's the kind of like continuation line. It doesn't need to start from, you can start from any column, it's not column sensitive language. Okay, so that's the, I'll just go back to the virtual memory thing. So you can see the VM start, VM end is over here, the constant. So we can use constant, it will be easier thing to do. The track frame address is also constant, so you can also have it here. This guy is a VM end plus 1, okay? So you can definitely also take advantage of that, VM end plus 1. Okay. If you don't plus 1, you have to add 1 in the end to be exactly the right byte. Otherwise, you miss 1 byte. So it still works if you miss a byte, but that shows that you're missing a byte. Okay. So is it important or not? Depends. Beauty is in the eye of the beholder. That look at your code. I guess at work or when you interview, they say, you miss a byte here. Does it matter? So, if it's a byte overflow, that matters. If it's a byte underflow, it don't matter, right? So if you build the traffic not up against the end of the virtual memory, but slightly lower, that is, okay. So you miss 1 byte here, and not used. So your stack pointer will start from here after popping the traffic. If you build the traffic here, okay. So the VM address on traffic is, says from the top of this, it should be 1.5 gig. Like that. So this minus the size of the traffic is where this should be, okay? So this drawing is, so it should be fully filled up like that. So that's the size of traffic, okay? So if you start from VM end, the VM end is minus 1, okay? It's inside here. So that's the phi F. So in minus traffic, it will be a little lower, okay? 1 byte lower. Anyway, this is what we said ourselves for the virtual running process. Okay, virtual running process. 2 integers are needed to fit our bill because we want to not up against that. When we have arguments and returning point, we will lower that even further. Okay, so this is what we want to do. This is a virtual address. We're going to push into the PCB of the new PID. That's the exit service. Okay. And then the traffic pointer. Traffic pointer equals this. Okay, will equal this. Okay, so inside the traffic, the EIP, it will equal to VM star. Okay, so this will equal to VM star. So that's also virtual. Okay, when these two addresses virtual at the beginning, the CPU fetch traffic to load will need a translation table. And when execution traffic popped in the CPU register, this register will have the virtual address here to fetch the first instruction. Okay, so that's a half a gig of 500 meg, and that's a 1.5 gig. The end is 1.5 gig minus 1 byte. All right, so we say we're going to have translation table to help us do this. All right, so let's look at the web page. This is the cost. Okay, so the final frontier. I have a test C here, testing the size of function cannot be obtained, but we can, yeah. So that's the, but we have this thing in CSC60, let end out text, end out data, and end. You remember these two, these numbers? Include the, we don't need to include anything. In the standard IO.H has already included the media thing. So what does that mean? That means these are virtual addresses you want to find out. Okay, so it's a little off the side, but that these are virtual addresses as you compile this and run. What happened is that the virtual process, okay, so very big, you know. How big is that? So you want to find out. Definitely you can print the main, that as an address, that's your main function, starting from where. But where does it end? It ends at the eText, okay, end of text, okay. So the eText is given, is inserted into your code, okay, as a global variable to set. And the address of this is a character, okay. But the content of that character is not used. It's actually used as a marker that your program can access the address of this. You print address on eText, you will see, oh, that's your code. Your code ends at that point. You know where it starts, but you don't know where it ends because you have subroutine, etc. Okay, and then that's why your first function, if that's the main, then that will be the name you want to print to get the first starting address for the code section. If you have a subroutine listed first in your program, and that will be the subroutine. Okay, subroutine, that is the first one. If it's a single .c file, if it's a multiple .c file, depends on the makefile sequence. The makefile listed which .c first, and then which function inside that first. The first function address is the one you print. You know where your code starts. Text, that is. This is the end of text. Okay, and then we have end of data and end. Okay. E-data is the constant, and then the end is the heap end. Okay. Heap end here, global data ends here. Constant. Okay. So these are already in the system. When you compile your code, you can print them, and they are the C runtime library insert for the C code to know the virtual address of itself. And then from the end is all the way to the end of what the system set. So the system will say the EIP starting from half a gig, and then let's see. You can also at the very beginning do an ASN to see ESP. Okay, you can also move ESP to an output X and then return X. Make your own. Make your own, little ASN macro, and then so you can print X. When you print X, then you know that at the beginning, your stack pointer at the top, okay? To use the stack, then you know that virtual address is the limit of your virtual space of your program code, of your process, okay? On ATOS, on Athena, on Titan, on whatever system, okay? All right, so anyway, so this text file just show you something that you can reveal the runtime of your process, your own process. Make sense? Yeah? All right, at the end of semester, we're all very, very tired. So, yeah, the last thing to do, right? Question?
For the, my brain just kinda caught up too. So for the trap frame for the VM, that, the pound define for it, you're saying that we can take the end of the VM, wherever it ends, right? And add 1 to it, and then subtract the size of trap frame and the size of it and get the same thing effectively.
Our VM end is it needs to +1.
Right,
Minus the trap frame type.
so that's the same thing as saying 2 gigabytes minus.
Yeah, it's the same thing. Okay. Yeah, it's a constant. 1.5 gig. It is same because 1.5 gig minus the size of trap frame minus the 2 integers. Well, actually, some people are pretty smart. They look at the trap frame as how many elements we have here? 12. It's actually array of 12. Okay. So in this sense, that this becomes the number 13 and 14. All right. So basically, it's the size of what am I saying here? 12 and 13. It's from 0 to 11. So we have 12 elements here. Each one is 4 bytes. So treating like an array will be easier to do things like this. So basically, it's the 14 integer size, right? If we define traffic like an array, then the element 0, element 1 will be what? Name will be what, okay? But we use like a structure. Structure gives us more descriptive name, EFL, CSEIP, okay, register name. But you can also use the C programming syntax to go around that, like we did with process states. We have a process state that in C code is an enum. You had when we B0 the PCB, it was 0. So it's avail, right? Avail. And then that's a 0, constant 0. Because when C enumerate number from 0 to the default. And then what's next? Ready, run, sleep, etc. Okay? And then that means by the default, they are this constant. Basically, it's the same as you define constant into name. Okay, when you mention this is a number actually. Okay, so it's defined ABAIL 0, define ready 1. Okay, etc. Okay. Also, C allows you to syntax that you can start from a different number. I will start a val with 3, and this one will be 4, consecutively increment by 1. Okay, you can also start with a different number, and like that. So it's the same as define actually. Okay, so we use that to type def the state type. Okay, so the state type. State type are actually numbers. Okay, very small range. So what is that for about this traffic? The traffic, you can define it like an array. And then you say, okay, the first element is what? The second element is what? Okay, ESI, EDI. That's the EDI, that's the ESI, and then all the way down to the last one, we listed it will be EFL. Okay. Okay, so you see, this is from low address to high address. In the listing of structure, in the code, that will be EFL listed down, okay? And the spread out in the stack, it will be towards the high address, okay? So that's the last one to pop. Then you can replace this, yeah, with constant names, okay? You can enum the traffic array type, okay, with the name inside it, EDI, ESI, etc., all the way to EFL. And then you can use that inside here. So you have the best of both worlds, okay? Like an array, and then you can use the name as the index. Okay, it's not that you have to remember the number, all right? Make sense, yeah? So this is how we're going to, if you use this in the last phase, also help you with the names of 5 different pages, okay? So if you say, okay, I have the 5 different pages, so the page, I need to have a TT page, I need to have a IT page, okay, I need to have a stack table, instruction table, that is, and then I need to have a instruction page, I need to have a stack page, 5 different pages, and then the index is 0, 1, 2, 3, 4, the index, okay? And what's containing inside could be a page number, okay? The page number may not coincide with 0, 1, 2, 3, 4, only for the first process. The second child process in the second terminal will start from 5, 6, 7, 8, 9. And if that exit, you start another one from another terminal back to the first terminal, it will get following the page available number Q, page Q, it will start from 10, 11, 12, 13, okay? But whatever they have got it in here, we store it and use in the source code, and TT, IT, ST, IP, SP as the index numbers by name. All right, so kind of like a hash table, yeah? All right, so but you don't need to use it if you don't understand it. I'm just saying that this is the tip for practicing to learn better become better programmer using C. Okay, so that's the thing. When you program in C, you don't program it like Java, and then you know what is in C that are goodies, and then you can apply them to do things like this. Okay, exact pointers, bitwise operators, and whatnot, and macros. Okay, and the enum. And besides the structure definition that you already know, structure definition is just like making class. It's not too hard. All right, make sense? The bitmap operator, the bitwise operation is very useful in this phase. When you want to get the first 10 bit or the second 10 bit, you can apply a mask, bit mask before it. Okay, so that's also a C only type of thing. Okay. And then you have the virtual address. Yeah, you want the first 10 bit. Okay. Because why? Because that is the entry in the translation table, the main table, which number, okay, that needs to be set. And what we have 2 very big virtual addresses. The traffic pointer in the VNTF. That's one big one. And in the traffic, EIP is a VM star. Okay. So we need to know the first 10 bit of this in order to know which entries to set in this translation table. In expectation of MMU, we'll look into that. MMU translate this, definitely we'll look into that. Translate this, we'll definitely look into that. Okay, so there are 2 entries we need to know. Where are these 2 entries? First 10 bit of this table, this address and this address. Okay, so you have to get the 32-bit address to give you the first 10 bit. Is that a right shift 22-bit? Okay, right shift 22-bit. But you had a problem like arithmetic shift and non-arithmetic shift, unless you design this as unsigned, okay, unsigned, right shift. Otherwise, it will fail in sometimes with one, okay, that becomes negative value, all right? So the best way to do it is to mask out. So we're going to mask out with O0 here, with OR, right? So this is going to be, and this is gonna be, wait a minute. We're going to mask out, we should use the AND gate, okay? Then this one should be O1 here, this is O0. Okay, so when it comes down, it's what? It's O0s, yeah? It got to be forced to become O0. And this is still not changed, okay? So the X is not changing. That's the AND gate, the bitwise AND, the operator in C. This is how I did it. Okay, so that's first 10 bit. Okay, first 10 bit. Okay, first 10 bit. How do you move it to the right safely? Anyway, divided by this big number. That's the thing is right shift, right? Right shift 22 bit. Right shift 22 bit. And let me take a peek out my code. I'm getting old, right? Getting senile. Okay, I'll give you a snippet of my code. How's that? Macro, maybe we should even get a macro to do this too, yeah? So define a macro to do this. Oh, I still did. That's terrible. I use the constant here, I still right shift 22 bit. Still do the shifting. And so why bother? But I use the BN star though. So I have the second. So this is what your code may look like. Okay, you don't need to do exactly like mine. Okay. BM star Why should I put it in a real small window? Allocate 5 pages. You can see I use the macro. When I need the address, I just use the macro. I put the address into the PCBTT. That's where we're going to give it to the MMU. Okay, set the MMU. And then before the prod loader call with the traffic address, which is a big number. So we got to set the MMU to use this table. We're going to build this table, okay. B0 that page, so the entries can be O0 out. And then we can copy the first 4 entries from the OS, and we're going to set the first entry and and 2 entries in the main table. BN star, bitwise, and FFC. That is the first 10 bit is 1. Okay. If you have 10 1s, that's FFC. Okay. 4F, 41F, 41F, 2 1. That's a C. We got 1100. Okay. 1100. That's C. All right, and then the BMN also does that. Okay, we have a flag to set, bitwise or hex 003. Okay, I'll explain this. All right, so let's get back to here. And the entries to send. All right, so you can see that was first 10 bit. First 10 bit. If you do it like this, whatever virtual address that is, you will know the first 10 bit. In our case, that this guy first 10 bit is gonna be here. This guy first 10 bit is gonna be this entry. In this translation table, there are 1024 entries, and this number is 128, 383 in decimal, okay, in decimal. And that comes from the, okay, so that comes from the 20000000. And you can see that each digit has a decimal is 4-bit. So it's kind of like 2 0 and half on the half of the 0. So that is the 0010000000. Okay, so that's kind of a half, yeah. And then you can definitely see that's a 1, 2, 4, 8, 16, 32, 64, 128. Okay, 128. First 10 bit 28, 128. You say, why are we doing this? Because that's what MAU. Okay, MAU is going to do it. Okay, MAU is going to look at the virtual address like that. The first 10 bit is going to look into the translation table. MAU also knows where this is. We're going to set CR3 with what the PCB just recorded the running process DT. Okay. Before we call the prod loader. Okay. So this statement says CR3 says okay. This TT is creating the XX service. Okay. We are doing it in the XX service right now. The purpose of making this TT is to set CR3. MAU will use this TT by being set with a set CR3 call to use this table to translate the virtual address. The virtual address coming in, the first one is gonna be this, okay, in the prod loader. Because prod loader is going to switch the stack pointer to this address to pop traffic. Okay, to pop traffic. This is where to find the sub table, first 10 bit. So we're going to have the sub table address here. Okay, so the top sub table address leads us to the sub table. All right, so this has a real address we want to put in. So basically, we're going to put the IT, okay, instruction table address here. Okay, put IT address here. And this one, we're going to put the stack table address here. Okay, like that. Wait a minute, this one's IP, this one's stack table. So the first 10 bit of this guy is 383. So MAU is going to look into 2 entries to get the stack table address, and the instruction table address. All right, so they are here. Okay, whatever the DRAM pages they are here. This is the instruction table and the stack table. And the second 10 bit, okay, second 10 bit is going to use as the subtable entry number. Okay, subtable entry number. And in that case, it will be all ones. All right. In this case, it will be all ones. Okay, so here we know that, okay, it's either 128 or 383. And this one is gonna be followed by all ones. And the virtual address. Okay, no, this one's gonna be all zeros, sorry. 200 is all zeros. Alright. So the second 10 bit is all zeros, meaning that the instruction table entry 0. Okay, so entry 0 is going to be looked up by the MAU to get the real address of the instruction page. And then the last 12 bits, all zeros. Then that is used to look for the instruction. Okay. So the first instruction. So basically we copy the child stuff here. Okay. We copy the child stuff here. Not the 4K byte page we copy to anymore, but we copy to this instruction page. And we're going to build the stack page here. Okay. Stack page will build here. And this will be the 2 empty place. This is the 2 places we're going to put the argument, which 0 null, and then the traffic. Okay, the traffic. So after the traffic is loaded, the EIP will point up to a virtual address to fetch the instruction. And the traffic itself is at the address, first 10 bits, 383. That has a stack table address. And then the second 10 bits, 01s. 01s means it's 1023, okay. 1023 will have the address for the stack page. Okay, so there will be the address of the stack page table. Starting byte of the stack page, okay byte. And then the rest 12-bit will be inside here, the beginning point of the traffic. Okay, the real address. Question? Yeah.
So you're saying, in order to get this, you're gonna mask it off, and then shift it by 22, then 12, and then take the last, mask it again, and take whatever's left over and put it.
Yeah. Yeah.
So it's 22, and then the instruction table, and 12, and then the ST, and then the last 12.
A different mask to get the second 10. Yeah. And this mask, the mask, this 10 bits, 1, others are 0. So you can mask out other bits, but you got to right shift 12 bits. Still need to right shift 12 bits.
So is it different mask or the same mask?
Different mask.
Different mask, okay.
Yeah. So there are 1, 2, 3, 4 entries to build. Okay. 1, 2, 3, 4 entries to build, and there are 5 DRAM pages to allocate. 5 of them to allocate. And the stack is built over there, 1 page, and then the instruction copied to 1 page. Okay, separate them. They represent the virtual space, the beginning and the end. Okay, these 2 pages. But the tables in the middle, this one is the main table. Okay, main table has 2 entries pointing to 2 subtables. Other entries are all invalid. Okay, because they are all B0 at the beginning. So all the entry flags are invalid. So the entry flags we need to set are just the last 2 set to 1. Okay. The last 2 flags we set to 1 are the rightmost 2 bits. Present bit is set to 1, and then rewrite set to 1. Okay. Other bits we don't need to use. So we can OR a hex 003. Okay, hex 003. Because it's 12-bit flags. Okay. Each entry has 12-bit flags. Alright. Each table entry has 12-bit flags. We're gonna set to 00011. Same 00011 and 00000, all 0, the last 2 are 1. Alright. So that completes the building of the translation table. Okay. And the process can move along, go to run in the virtual space happily ever after. Alright. So you see, it's because MAU hardware is doing that. That's why how we set this like that. Okay. So we have allocated 5 DRAM real pages. The table will give us the virtual. What is virtual is the entry number taken from the virtual address. Okay. Finally, find the instruction page that's actual. Stack page, that's actual. The last 12 bits are not changed. It's inside this 4K file. Okay, inside this 4K file, where to fetch the instruction, where to fetch the traffic. Okay, 12 bits because 4K file, to address a byte, you need 12 bits. Okay, so the first 10, second 10 are virtual, again, right? So don't get confused by where's the virtual part, the first and second 10. All right, they are not in the table. They are the index in this array table. Okay, makes sense? Each one used like an index. Inside is the real address, of course. Okay, the address of a subtable, the address of a real page from the subtable. All right. So you're all very excited to do it. All right. So, okay. Don't have a delayed start. Okay, get a head start. So let me know if I have any question next Monday.
Let's do this weekend.
We got final in 2 weeks.
Do this weekend or
No, next weekend.
next weekend?
You have 2 weeks of time, so you can wait till next Sunday.